Hey guys, and welcome to another AS Mechanics video. So this is the actual last topic before we can move on to doing some past papers for the Year 12 content, and then of course I'll start uploading Year 13 content as well. But of course we've got quite a few papers to get through at the same time. Now you might notice we're only going to go through 4 questions in this topic, and the reason for that is that this comes up in every single past paper, so we're actually going to get a lot more questions done than you might think. And this is a fairly involved topic. While it is called pulleys, it's basically connected particles and also a little bit of SUVAT and also some resolving forces all in one as well. So we're going to be using pretty much everything. And of course we're going to be drawing diagrams. So if we read the question, two particles A and B have a mass of 0.4 and 0.8 kilos respectively. They're connected by light and extensible string, so remember what that means. Light means that the tension is the same throughout, and inextensible means that the acceleration is identical. So, for example, if particle B moves, then particle A moves with the exact same acceleration at the exact same time. Particle A lies on a rough horizontal table, 4.5 meters from a small smooth pulley. So what this means is that there's no kind of force lost due to the pulley. So what that means is the tension on both sides of the pulley is going to be identical, which is fixed at the edge of the table. So we can probably start drawing out some of this stuff. So if we draw out our little flat surface here, oh, that's terrible. Let's try again. There we are, and then we draw that. And then we have a pulley like so. We have particles A and B. So A is the one on the table. So I'm actually going to draw it as a box, just for personal preference. Technically it should be a circle, but it doesn't really matter that much. And then obviously the other one's going to be dangling over the edge. And we're going to join them by a little string like so. Cool. And then we have, this is 4.5 meters, so I am going to add this onto the thing because they wouldn't give me the information if it wasn't useful at some point in the question. And we have the masses, so particle A is 0.4 kilos, so that's going to be 0.4 g. And particle A is 0.8 kilos, whoops, which is going to be 0.8 g. So because they're connected by a string, we're going to have tension. Now tension in a pulleys question looks like this. Now again, remember, when you stretch something, tension acts to unstretch it. So this string is being stretched over the table. So it means tension is going to act like so. It's going to act upwards for particle B. For particle A, it's going to act to the right. And hopefully this makes a bit of sense, because if we look at this situation, if it is accelerating, then A is going to accelerate to the right and B is going to accelerate down. Because there's no other way that it would make sense, right? It doesn't make sense for B to accelerate upwards and A to accelerate to the left, because there's nothing causing that. So the thing that's causing that is going to be the tension because of the weight. So we've got that done, and it says that it hangs freely. String taut. Taut just means that there's no slack in it. 0.5 meters above the ground. So what we could do is also draw this and say 0.5 meters. Now of course with the acceleration we don't know it, but if it is accelerating, it's going to be accelerating down and to the right. And anything else? A frictional force opposes the motion of particle A, so that's going to be going this way, which is 0.08 g. That's quite nice of them to provide. As the systems release from rest, find the acceleration. Okay, so just like with connected particles, what we can do, and this is a very nifty trick, is we can actually resolve them separately. Okay, which is extremely useful. So I'm actually going to move this diagram over so I can actually draw on it. So what I mean by that is we can actually resolve particle A and particle B separately. Now the key part here is I can't just combine them. Do you remember how in the connected particles thing, because they're moving in the same direction, we were able to treat them as one big particle? In this case, are they moving in the same direction? No. They're moving horizontally and also vertically. But it's also, it's not in the same dimension either. So, we can, though, resolve them completely separately, which is really useful. And 99% of the time, you want to resolve particle B first. The one that's hanging over the edge first. Why? Well, if we have a look, it has fewer unknowns. So, in short, with pulleys, you're going to resolve both particles anyway, because generally speaking, there's multiple unknowns. So let's start with this. The reason why I said there's multiple unknowns is because in this case there's technically a resultant force, a normal reaction force over there. So let's resolve particle B, And again, I'm going to take downwards as positive because I always take the direction of acceleration as positive. And because we don't know if it's accelerating or not, it's going to be F equals ma. And this is how we're going to figure out if it is accelerating. So the forces at the moment, we have 0.8 g acting downwards, minus the tension is equal to the mass, which is 0.8 times a. And again, maybe that's 0, maybe that's not, but we don't know. Then we're going to resolve for particle a. And I take direction of acceleration, so to the right is positive. Again, I don't know if it's accelerating, but if it is accelerating, it's going to be going to the right. And again, we use F equals ma. And here we have t minus 0.08 g equals 0.4 a. So we have two equations and two unknowns. And if we have a look, something very interesting has happened. Here we have a negative t and here we have a positive t. So if I were to add these two equations together, so if I write them on top of each other, 0.8 g minus t equals 0.8a. And then here we have 0.08. Sorry, no, we don't. I don't know what I'm writing that for. We have t minus 0.08 g equals 0.4a. If we were to add those two equations together, we would be solving this simultaneous equation by elimination, which is really useful. Hopefully that makes sense. Technically, you can use a calculator to solve simultaneous equations, by the way. So there is a simultaneous equation solver, but I would recommend doing it this way. So let's add these two equations together. We get 0.8 g plus minus 0.08 g. So that would be 0.72 g, because it's just going to be subtracting. The t's cancel out, which is exactly what we want, equals 1.2 a. So a is just equal to whatever 0.72 g divided by 1.2 is. So let's have a look-see, shall we? 0.72 times 9.81 divided by 1.2 gives me an answer of 5.886. So we normally round to three significant figures, so we have 5.89 meters per second squared. And that first part is probably worth 3 or 4 marks. I do have some exam questions coming up. These are exam style questions, but they are made a tiny bit simpler just for the purposes of demonstration, but I do have some more coming soon. Perfect. The common mistake I see is that people kind of assume that this pulley, this part of the pulley, is going to accelerate downwards at 9.81. But that doesn't make sense. It's being slowed down by A. Okay? Perfect. So now we have the acceleration. That's really, really useful. It says find the time taken for B to reach the ground. So this is where SUVAC comes into place, because our acceleration is going to be constant until it hits the ground. But that's fine because it says the time taken for it to reach the ground. So let's write out all the variables we know. Well, the displacement, the height above the ground, is 0.5 meters. What's the initial velocity? Well, it says it's released from rest. So the initial velocity is going to be 0. Do I know the final velocity? Nope. Acceleration is 5.89. And lastly, we have time is equal to, well, that's what we want to work out. So let's write down the variables we want / have. So we have SUAT. So S equals UT plus half AT squared would probably be the one I use. Half A. Because again, don't forget, it's free fall, right? So it's normally going to be the S equals UT formula. And of course, for the first equation, for the first term is going to be 0. And that means we can rearrange T to be T is equal to the square root of 2S over A. So square root 2 times 0.5 over 5.89. This is going to be quite a small number, which, fair enough, it's only moving half a meter. So square root, that's going to be 1 over 5.89. 0.412 seconds. Like so. Perfect. Now here's where things get a bit more interesting. We have here a particle. Now it says the total distance travelled by A before it comes to rest. So first of all, since it's attached to a light inextensible string, it is going to travel the exact same distance as B initially. So it's going to have half a meter already locked in. Okay? Because again, that B has pulled A half a meter before it hit the ground. Now when it hits the ground, the string is now not providing a tension force. There's no tension here. because it's gone slack. B is not pulling anything anymore. Hope that makes sense. So what we have to do, and this is a bit tricky, is we have to work out the velocity of A, and then we need to use the fact that it's going to be decelerating, find out the distance, and add it on. This last part is normally worth 5 marks, so it is a bit involved. So, first thing I'm going to do is, and again, because this is an inextensible string, whatever the velocity of B is going to be whatever the velocity of A is, correct? Because it's joined, okay? So, we're going to work out the final velocity. Now we can use any equation we want. So I'll probably use v equals u plus at for this one. So the velocity is going to be, once again, that's 0. So it's just literally going to be 5.89 multiplied by 0.412. So 5.89 multiplied by, our answer gives us 2.43 meters per second. So again, just to give you context, B has dragged A and allowed it to get to a speed of 2.43 meters per second. It's then hit the ground, so now it's no longer being dragged. But now we're going to have this situation here. So after the string is slack, and again, this is where Pulleys gets tricky, but we're going to do a lot of practice with this, so it's fine. It now behaves just like a regular old box, which has a mass of 0.4. It has a deceleration, or sorry, a frictional force of 0.08. And there's no other forces. So now what we have to do is work out the acceleration. Now how do we do that? Well, it's actually quite nice and easy. It's just F equals ma. The only force we have is 0.08. Now which way do we want to take as positive? Well, we could take forwards as positive still, right? If we wanted to, because it's going to be decelerating, that would make a bit of sense. So we have minus 0.08 g equals 0.4 a. So a is equal to negative 0.08 g over 0.4. Let's put that in and see what we get. So we get, let's put it in brackets just to make sure everything goes well with the calculator. Whoops, I pressed X, not times. There we are. Over 0.4. And we get minus 1.96, I'm going to call it. Okay. I know this is a lot. So again, the box has already travelled half a metre, and in that time has accelerated to 2.43 meters per second. It's now slowing down because the string is slack, there's no forward force. So if we set up suvat now, S is I don't know, it's not this half a metre. This half a metre is before. Remember, and this is the key thing, when we use suvat, we're using constant acceleration. When we did this half a metre, the acceleration was positive 5.89. Now the acceleration has changed, we have to set up new equations. The initial velocity is 2.43. What would the final velocity be? It would be 0, because we're seeing how far it travels in total. A is negative 1.96, and T is, I don't know and I don't really care. So S, U, V, and A, so the equation that comes to my mind is V squared equals U squared plus 2AS. So V is, of course, 0. So now if we push this everywhere, let's say S is now going to be U squared, negative U squared, over 2A. So that is going to be negative 2.43 squared over 2 times negative 1.96. Like that. Cool. Minus 2.43 squared over 2 times minus 1.96. Gives me 1.51 meters, let's call it. So again, it travels 0.5 meters by itself, and then it slides for another 1.51 meters. So the total is 0.5 plus 1.51, which is of course 2.01 meters to 3SF. That took 15 minutes because of all the explaining, but I will point out that all of these parts together usually amounts to about 9 or 10 marks, sometimes up to 12. Okay. So we're going to look at the other situation they can put you in pulleys. There's only two, which is quite nice, but you may notice the actual structure is the same. So the first question asks you to find tension or acceleration. The second one, it kind of implies you need to work out some kind of speed. And the third one is we're still going to do the same thing. Find the greatest height. So otherwise, we're going to find the total distance travelled, which is the same thing as the first one. And that's what you're going to notice with every single pulley question. So although it does seem very, very tricky, once you kind of do it once and you get it, you can do any one of these questions. The final part is always going to be something along the lines of find distance travelled. Some kind of distance. Now, okay, there might be a part D where it says state how you've used the modelling assumptions, but that's it. In terms of calculations, this is the kind of structure they're going to always follow every single time. So I said this is a slightly different situation because if you notice it doesn't mention any kind of table or horizontal surface, because this is actually just a normal pulley. So let me show you how it looks. That is a pulley, and then it's going to droop down either side, and this is where I actually use normal particles, and let's call them A and B. It doesn't matter which way around you label them because you will get the same thing regardless, and they are 4 and 3 kilograms as long as you label them with the right measurements, of course. Like I literally just didn't. As soon as I said that, I wrote the wrong number there. There we go. And of course the tension is still going to be acting upwards like so. Now the acceleration, which way does it make sense to accelerate? Well, it makes sense for A to drop because it's the heavier one. And again, because we have no tension in the pulley, that means that there is there's no way for A to not accelerate. Right? In this case, because it's smooth, A is definitely accelerating downwards, no question about it. In the first question we had tension, and tension we had friction, which could in theory stop it from moving, but in this case nope, no way, 0% chance. So they release from rest, cool, find the tension. So in the previous question it said find the acceleration, but if you notice we're going to be doing the same thing. We're going to be resolving for A and B separately, and then we're going to be solving for acceleration or tension. Now if I look ahead a little bit, it says find speed, which means we're going to need acceleration anyway. So I'm just going to work out both, because we will need it at some point. So part A, find tension. Well, let's resolve for particle A, and we're going to take downwards as positive because it's my direction of acceleration. F equals ma. So what forces do we have? Well, we have 4g going downwards. Subtract the tension is equal to 4a. That is my first equation. Then we have particle B, and we're going to take upwards as positive. And this is actually why I like being consistent. So technically speaking, there's nothing stopping me from taking downwards as positive again, realistically, but it means that I won't be able to eliminate it as easily. I'll have to use substitution, or I'll have to subtract or do something else. This way, all I need to do is add. Adding with simultaneous equations is less prone to error, because when you subtract, you might need to do like minus t minus minus t or something, which I know it doesn't sound super hard, but in an exam, lots of students make mistakes. So again, that's just another reason why I always take the direction of acceleration to be positive. So here again, we can see all we need to do is add, and this is actually quite easy. 4g minus 3g is just g, minus t and t cancel, so we just have g is equal to 7a. So in other words, a is just equal to a 7th g. So we've got our acceleration, which is we're going to use for part B. Nice, perfect. But that's not what we were here for. We wanted tension. So if I sub this into equation number 2 and move 3g to the other side, I get t is equal to 3 times a, so 3 a 7th of g, plus 3g. So you could work this out in terms of g. So in some mark schemes you might see them give answers as fractions of g. So in this case it would be 3 over 7 plus 3, so that would be what? 24 over 7g. So you could have it as 24 over 7g. And you'll find that in quite a few mark schemes, or you can, and that's just because it keeps it nice and a whole number, like it makes it a precise value. Or if you just did 24 divided by 7 times by g, that is also perfectly fine. Either way you want to do it. So I'm going to just leave it as a 3 significant figure number because it really doesn't make much of a difference if you take 3 sig figs. But that is our value for A. So we have 2 different values. Well, they're the same value, they're just written differently. That would probably again be for about 3 marks. When A has travelled a distance of 2 meters, it strikes the ground and immediately comes to rest. So again, it does tell you which one's actually going to be accelerating. It's A, accelerating downwards, dropping. Find the speed of A when it hits the ground. Okay, so if we do that, we have S is equal to 2 meters, U is equal to 0, it's released from rest, V is equal to don't know, and that's what we want. A is equal to 1/7 of G, and it actually tells me, it doesn't tell me the time. Cool. So V squared equals U squared plus 2AS is probably what I'll use. And once again, U goes to 0. Nice and easy. So V is just equal to the square root of 2 times 1/7 G multiplied by S, which is again 2. Excuse the really poor handwriting at times. So square root 2, and we have G over 7, so 9.81 divided by 7 multiplied by 2 gives me a pretty hideous number, 2.37 meters per second. So let's keep it as that. That would be a 2 marker. Pretty solid. And then it says, assuming that B does not hit the pulley, find the greatest height. So they've actually done a lot of work for us. A lot of work. But we still need to do some of it ourselves. So again, for C, I like to write that there is an initial 2 meters. We have the velocity, but once again, the acceleration is not the same. Otherwise, it would actually keep accelerating forever, right? Because it's just going to ping off into the space. The acceleration should be going downwards now. And why is that? Well, it's actually just a free fall question, right? It's actually not too bad. So if we look at particle B now, we have particle B as a downwards force of 3g, and that's actually it, right? So that means the acceleration is also going to be down. Now, the really useful thing about writing it in terms of 3g, let me show you, is because F equals ma, we have 3g equals 3a. So in other words, a is just going to be g. So that's actually one of the reasons we use g all the time, because it actually tells us what the acceleration is straight away. Now, remember, all objects on Earth accelerate with g if they're under freefall. So in this case, it's under freefall. In the previous case, it wasn't under freefall. It was being dragged along a surface. So in this case, it's of course going to be g because it's falling. So let's work this out. So S is don't know. And again, we're actually going to take upwards as positive for all of this. I know that means this will be negative and yada, yada, yada. U is going to be upwards 2.37. We're going to look at when V is equal to 0. A is going to be negative g. Why? Because again, it should be slowing down this object. And T, I don't really care. So again, we can use V squared equals U squared plus 2AS. Oop, get rid of that. And if we rearrange this for S, we get negative U squared over 2A. So negative 2.37 squared. I just had deja vu. I've done so many of these questions in the past that it's incredible. Perfect. So if you want, we can actually use an exact value. And whenever you can, you may as well use an exact value because it's fun. 2 times negative 9.81. Yeah, that's all good. 2 over 7. Wow, that's a really precise number. 0.286 meters. So in total, and again, you want to make really clear that you're doing a total. It's 2 plus 0.286. So I'm going to do that to 3SF, so 2.29 meters. So can you see how we're doing like the same thing again and again and again? It's quite nice. And we're definitely building up to that A2 knowledge, which is fun. And again, this kind of question will come up every single Year 12 exam, period. I don't think I've seen a paper that hasn't had it in there. But again, we're going to do every single paper anyway, so I'll be able to prove that to you. Hello there. Check this out. 7, 10, 13, 14 marks. You see what I mean? So they're between 10 and 14, sometimes even 15 marks, these questions. Pretty beefy indeed. But they give us a diagram, which is very nice of them. So which one's going to be accelerating downwards? Well, if we look out here, it says Q reaches the plane, so Q is heavier. So again, that's fine. All I'm doing this for is to make my diagram accurate, so it's not actually like it's cheating at all. You can't really cheat in maths, sadly. And that would be KMG, and this would be 3mg. We have tension going up. That's all our forces. K is less than 3. Oh, okay, so we could have just looked there. Never mind. It does tell us in the question. Particles connected by light and extensible, blah, blah, blah. Plus a smooth light fixed pulley. Yep, cool. The system's held at rest with the string taut. Blah, 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 blah. Same height above a horizontal. So that's a really key point here, is that they're at the same height. Which is probably why they gave us the diagram, by the way. They've been quite nice. System's released from rest, and... ooh, hello! It tells us the acceleration. 1.3, 1 over 3g. That is very nice of them. And for part A, it says calculate the tension. So once again, all we're going to do is we're going to resolve for both of these particles. So let's resolve Q, and we're taking downwards as positive. Whoops, there we are. F equals MA, the usual. We have 3mg going downwards. We have a tension going upwards. M is 3m. That's also a thing that some people make mistakes. They write 3a instead of 3ma. In this case, M is 3M, which is very confusing. I do 100% wholeheartedly agree with you. Let's do the same thing for Mr. P. And we have K. Actually, no, we have tension minus KMG equals KM. By the way, there's actually one thing that I want you to know. And I think it's really important for teachers to tell you this. I don't know how we're going to do this straight away. So, what do you do when you don't know? And bear in mind, there is a lot of mechanics questions where I don't know kind of the full method that will get me to the answer. So what do? You always resolve every particle in every direction that you can. At the moment, we're only really dealing with one dimension, right? We're dealing with up and down. Okay. But when we come on to A2, you'll find that you can resolve up, down, and left, right sometimes. So in general with mechanics, if you're stuck, if you just look at this and you go, I have no idea what I'm going to do, just resolve everything that you can. And that sometimes leads to a realization of what you can do. So let's have a look at this, shall we? It says we need to calculate the tension in the string. So that probably means we may need to work out acceleration. Actually, no, we know what acceleration is. So we have two unknowns and we have two equations, don't we? So what we can do is we can actually add these two things together, which I know is going to get rid of the tension, but let's have a look. 3mg minus kmg, so let's write that out. I know what you're screaming, but sir, isn't there three unknowns? You're a very clever person. There is three unknowns, but I'm going to show you why I don't care. And this, again, is why you should just do it. Because there's m in every single term, I can divide everything by m. Now, there's only one unknown. Cool, right? So, that's the kind of... I want to say it's the kind of skill that you need to develop, but you just need to have that confidence, okay? Resolve things in every direction, and then, start trying to eliminate stuff. And generally speaking, you'll come to a solution. Hopefully that makes sense. We can divide everything by m. So we have 3g minus kg equals 3 times a third is just going to be g plus k over 3g. So what I want to do is I want to move this kg over to this side and this g over to this side. So 3g minus g gives me 2g. And then we have k over 3 plus g plus kg. So that would then be, should we do that? It would be 4k over 3g. Get rid of the g's. So then we can work out what k is just by doing the opposite. So 2 times 3 is going to be 6. 6 divided by 4. So half it gives me 3. Half again, 1.5. Now again, that's not the question. However, look at part B. Show that k is equal to 1.5. Good. So we've actually done part B, which is fine. what we can do now is we can actually label that as part B, and that counts. So this is another thing that I really, really adore about the mechanics exams, is you have a lot of freedom. So you can do part B before you do part A, and use part B to do part A, and they have no qualms about that. So this is now my part B working out. So how would you do part A without doing part B first? Well, what you'd have to do is rearrange for K and sub it in. Pretty ugly, right? So instead, I've made my life a lot easier. We could sub this back in. Actually, can we? No, we can't sub it back in. All right. I was trying to be a bit lazy. So what we can do is sub this into this equation here and try and eliminate m instead. So doing that will give us the correct answer. But just so you're aware, you could have done rearranged for k or rearranged for m and subbed it in, and you would have gotten the tension in that way. But for this case, we need to work out the tension. So what I'm going to do is I'm going to sub in the k as 1.5 into this equation, just so we have it. So minus 1.5 mg equals 0.5. So we have 3 over 2 times a third, which would be 1 over 2g. So it would be 1 over 2 kg. Not k, mg, damn it. Alright, here we are. Move the mg to the other side, we get t is equal to a half plus 1.5, so that's 3 over 2 plus a half, so that'd be 4 over 2, which would be 2 mg. 2 mg, like so. Cool. So from here, we could either sub in that tension is equal to this, work out what m is, and then work out what g is, and would that actually help us? I think it would. Or we could rearrange this for m and sub that in. So what I could do from here is I could say that m is now equal to t over 2g and sub that into one of our two equations. Probably the top one because we rearranged the second one. So 3 t over 2g minus t equals 3 t over 2g times a third g. So gather all of the t's to one side. So here we have, if I factorize this out, factorize both of these out, we can get t over 2g minus 1. Factorize this t out, we get t minus it to move it to the other side. So I'm trying to do this all in one step because I'm being a tad lazy, I'm not going to lie. But we could move the t over and then solve from there. So let's go through that. So quick note, we were doing it correct. This is the actual final answer. So all we need to do is just mention that we've done part A down here and we should be done. So just erase it back to here, back to k equals this, do this first step, and then that'll be our answer. So means we will need to record a little bit which says t equals 2mg is the answer, by the way. So if you notice, we can't, if I were to sub this back in, I can't actually work out what the tension is as a number. And that's because in mechanics, we can leave our values as expressions, just like this. So this is actually completely and utterly fine. I can keep it as is. So that would be the answer to part B. Now for part C, it says state how you've used the information that the pulley is smooth. Well, we use that because the acceleration on both sides of the pulley is the same. So acceleration, both sides of pulley is the same. And lastly, we need to go through part D, which is a beefy 7 marker. So let's get started with part D. So after descending for 1.8 seconds, the particle Q reaches the plane. It is immediately brought to rest by the impact with the plane, and the initial distance, blah. So basically, these last sentences that they write here, it just means that it doesn't hit the pulley, you know? And in 99% of cases, it doesn't hit the pulley. They will say, like, will it hit the pulley kind of thing? So if it's 2 meters away and it travels 2.1 meters, then yes, it would hit the pulley, that kind of stuff. So it also has the answer in terms of g, which is good because our acceleration is in terms of g. So we're just going to leave everything in terms of g if we can. So it's the same question, but look at that, 7 bloody marks. That's a lot. Okay, So what we want to do is we want to work out the final speed of Q and also the distance that it travels. So if we look at just Q for a second, so let's look at particle Q. Then it has the tension going up, but realistically I care about the acceleration, which is a third g, and we also know that, so S is we don't know, and we do care, we do want that. U is 0 because it's released from rest. Let's zoom in a little bit. V is we also don't know. A is a third g, and T was, it told me, I just can't remember, it was 1.8 seconds. So from here, there's two things we want. I want its final velocity and the displacement, because that's going to be kind of the beginning distance. So let's work out V first, because that'll give me V is equal to U plus AT. And this is quite nice because U is just 0. So it's just a third g times 1.8. And again, because we want everything in terms of g, I'm actually just going to do a third of 1.8, which is 0.6 g. So then for S, what should we use? What would be a good one? You could use S equals UT plus UT plus a half AT squared. Yeah, why not? U is 0, and that means we get a half, a third G, T squared is 1.8 squared. So what I'm going to do is on my calculator is I'm going to put in a half, so 0.5, times a third, times bracket 1.8 all squared, and it gives me 27 over 50. Is that all correct? It is. Okay, it's a bit of an ugly number, 27 over 50 g. Let's leave it as that. So 27 over 50 g for S. So this is like the first part of the distance, okay? So if we look back at the question, the greatest height reached by P above the plane is 1.26 g. Well, we have, it's gone up by 27 over 50 g. Now, there is a bit of a stealthy nature to this. So, if you remember, P and Q were at the same height. Okay, so let me just draw out the situation that's happening. That's P, that's Q. And there's a floor down here. Now, Q has dropped 27 over 50 g. Yeah? That means P must have started off at 27 over 50 g. Correct? But now it's moved up. So Q has ended up down here, and P has ended up somewhere up here. So it's gone up by another 27 over 50 g. So it's an additional part. I can imagine that potentially being a bit confusing. So realistically, this distance is actually doubled, because remember what it's saying, above the plane. It starts off already 27 over 50 g, and then because Q has gone down 27 over 50 g, this side must go up 27. So in total, it's two lots of 27 over 50. I hope that makes sense. I hope that makes sense. So if we double that, we get 1.08 g. You can probably see why it's like 7 marks now. So now what happened is P is no longer being dragged up. So we need to now work out the new acceleration. So we don't have a value for tension, but that's fine because tension has disappeared. But we have kmg. And if you look, our acceleration was in terms of g beforehand anyway. So if we write, so let's draw out the situation for P now. It's going down by kmg, but if you remember, we worked out k as 1.5. So it's 1.5 mg. And that's it. So if we do F equals ma, again, we want to take upwards as positive, if we can. So we have negative 1.5 mg equals, 1.5 m times a. Those two things cancel out, and we're left with a is equal to negative g. Now we do see that once more. So S is equal to don't know. U is equal to 0.6 g. Our final velocity is equal to 0. A is going to equal negative g. Yeah, this should be fine. And t is equal to don't know. And we want s. So v squared equals u squared plus 2as, just like we've used before. So v is 0. So our value for s is going to be negative u squared over 2a. So that's minus 0.6 g squared over 2 times negative g, so negative 2g. What I can do here is I can cancel a g and one of those g's out. So let's do that. It's going to be cancelling that and technically the squared. So it's going to be negative 0.6 squared g over negative 2. Cancel out the negatives. So that would be 0.18 g. And okay, that works perfectly, because if you notice now, the total height, or the max height, is 1.08 g plus 0.18 g, which gives us the 1.26 g that they were talking about earlier. 1.26 g. Now, here's where the mistakes would obviously be made, is the timesing this by 2. I've taught stats and mechanics for 6 years, and I have seen this question before, but I did actually kind of forget about it. But then when I went through it again before the lesson, of course, I did realise very quickly. So with mechanics, the wording's very careful. It's very particular. Now, this for 7 marks isn't actually that bad if you think about it. But again, the timesing this by 2 is definitely where people mess up. And another thing that people mess up on is when the answer is in terms of g, they don't do all their working out in terms of g. So what they'll do is they'll, let's say for example, instead of 27 over 50g, they'll put it as a decimal. So I actually don't even know what that would be as a decimal. Times 9.81. And the problem is now they're dealing with numbers that are quite long, and so they might round it. So then when they then try and put it in terms of g by dividing by g, they've got the wrong answer. Like they, instead of getting 1.26, they might get 1.24, 1.25, or 1.27. And then they go, where have I gone wrong? It's like, you haven't gone wrong, it's just that you've rounded. So keep that in mind. If they give you the answer in terms of g, do all your working out in terms of g. It's not that bad. If anything, it makes it slightly easier maybe. But I hope that makes sense. That was a very long question, 14 marker. Not bad. We've got one more and then we'll be done. Once again, we have a pretty annoying, in terms of length question. If you look at the whole paragraph, yeah, you need to get used to this, unfortunately. They do give you quite a bit of information. But what I'll do is I'll start adding some of the forces that you know are going to be here. So 1.5 g. It's obviously going to be accelerating downwards because, again, it can't really accelerate left. So 2.5 kilos. So let's put that force there. It's a rough table, so let's put the friction there. The tensions, of course, going this way and this way. Of the frictional is K newtons. So that frictional force here is K. System release from rest. Okay, let's make sure we haven't done anything else. And then after release, Q descends a distance of 0.8 meters in 0.75 seconds. By modeling P and Q as particles, calculate the acceleration of Q. Now, there are a few things you can consider. One of which is, of course, using SUVAT to work out the answer to this. So we have S, we have T, and we have U because it's from rest, so we could work out what A is from there. Bit cheeky, but you can absolutely do it. By doing V equals U plus, or by doing A is the change in velocity or something, or V squared equals U squared plus 2AS, any one of these things. But I think, it makes sense that even if you're not sure, you may as well just resolve for P and Q and see what happens. So, for this question, because it's specifically asking me for acceleration and they gave me information in terms of SUVAT, let's do SUVAT. So A part I, we have S is equal to 0.8, U is equal to 0 because it's released from rest, V is equal to don't know and I don't care, A is equal to don't know but I do care, and T is equal to 3/4 of a second. So SU, A and T, the equation that comes to my mind is S equals UT plus half AT squared, which again, because it's in free fall, this is an equation we use all the time. That goes to 0. We want A, so let's quickly rearrange. Times both sides by 2 gives me 2S. So it'll be 2S over T squared. So 2 times 0.8 over 0.75 squared. Let's have a look, see, and see what happens. 2, 0.8, close brackets, 0.75 all squared. That gives me an answer of, oh god, 2.84 meters per second squared. 3 marks! 3 bloody marks. It's not bad, is it? Not bad at all. Part 2. Show that the tension is. Okay, so again, this is where we're going to actually start resolving. Now, again, I would always recommend resolving P and Q if you're unsure, but if we have a look at this, P has 2 unknowns, T and K. We know what A is now, whereas Q only has 1 unknown, tension. So let's resolve for Q, and I like to take the direction of acceleration, which is downwards, as positive. So again, we're using classic F equals ma as usual. So the downwards force is its mass, its weight, which is 1.5 g, minus T equals mass, which is 1.5 times 2.84. So if you were to rearrange this, you move the T to the other side, move this thing over to this side, you get that T is equal to 1.5 g minus 1.5 times 2.84. And we may as well put that in brackets because we obviously mean to work that out first. Not too bad, I hope. So 1.5 multiplied by 9.81, subtract 1.5 multiplied by 2.84 of 10.455. Let's say it's 10.5. I should actually put that these are to 3SF because they are answers, so they should realistically be given estimates for accuracy. So that's 4 marks! Oh, hang on, it says 10.4 to 3 significant... Yeah, sorry, 10.4 then, that's totally fine. If you're wondering why I got 10.5 instead of 10.4, it's because they used 9.8 as their value for G. So we did get the right answer, just in case you're wondering. The reason why I always use 9.81 is because in some exams and some exam boards they use 9.8, some they use 9.81. So it looks like they haven't mentioned it, but they mention it at the beginning of the paper. The annoying thing is in some papers, some years, they say 9.81, or in some questions they say use 9.8 or use 9.81. So in this question, obviously they meant for us to use 9.8. So that's why I got a slightly different answer. But I promise you, in the question or the paper, they will tell you to use G is equal to something. 9.8, 9.81, whatever it is. That's 4 marks! 4 marks! Come on. It's like 3 lines of maths, and it's easy maths too. Not bad. Not too shabby at all. And that's, again, why I love mechanics. It's my favourite topic in maths. Find the value of K. Well, again, we're going to be resolving P. Again, we always resolve P and Q eventually anyway. And we only have one unknown, which is K. Nice and easy. And you might also notice that in these mechanics questions, they give you a lot of information for free. So, for example, our questions were show that here. So that means if you didn't get this part correct, you can do part C still. So we have T minus K. So T is 10. Well, it says 10.4 to 3SF. Let's just use the value they give us. Minus K equals mass. I can't remember the mass. It was 2.5 times the acceleration, which was 2.84. Yeah. I've got the memory of a sieve. All right. So then K, if we just rearrange this, is going to be 10.4. Actually, K equals 10.4 minus 2.5 multiplied by 2.84. Not bad. And this was an actual exam question, by the way. So I know I normally say I won't put like all of the exam questions in there. I haven't put all of them, by the way. But I just wanted to let you know. And in the textbook, by the way, there are previous exam questions if you're interested. But after this is 3.3. We are doing every single past paper in existence. Part B, how have you used the information that the string is inextensible? Simple. The acceleration, both particles accelerate at the same time. That's it. And that's it for pulleys. My goodness, and that's it for AS mechanics and stats. We're done. So it's not that long, which is really good. The bright side is A2 stats is 3 chapters. It's really small, which is really, really nice. Mechanics is a bit longer, but what we're going to do for now is we're going to do a bunch of past papers. And what I will also do, and you might notice we're going to finish really, really early. So what I'll do is I'll do year 12 stuff, as in the past papers, every single one. That should take us until about January, because there's quite a few papers. Then we're going to start A2. But before your actual exams in May, June, July time, I'm going to go back and do some predicted papers, some specimen papers, Solomon papers, basically papers that are extremely difficult. I'll even do some of the really difficult questions in the textbook, the challenge questions, just to prepare you for your exam. Okay, so we will go back to year 12 stuff. But other than that, hope you have a wonderful day. I'll see you in the next one.